So today I try to present some link between generative modeling with associated SDEs, some optimal control, and the optimal control comes into account through the means of these HJB equations, and we discuss their solutions based on compression tools that rely not on neural networks but on Lorenz manifolds. So let's start this joint work together with David and Martin, Max, and Claudia from a few billion. So what is the goal of this talk? So we aim to sample from a density. So we are not in the regime that we have any data, right, of sample data. We want to have a density of structure x to the minus some potential phi. And for the sake of simplicity, we assume this potential to be smooth enough, let's say C2. And we see this is related to appearing for Kaplan equations later. And what we will do is we devise a sampling strategy that is based first on some score-based SDEs or ODEs. So this is a link to the generative modeling. And we will approximate the score through the means of this solution of this Hamilton-Jacobi-Bellman equations. So for the interested reader, here's the work that was put on archive in the early of this year. Okay. So as a simple motivation, we saw in our first tag, when does these potentials usually appear that are known up to a constant? And this is classical, maybe my bias background is a Bayesian inference. So by Bayes, we have some observation, we have some forward model and some noise. And by Bayesian theorem, basically appear to have some likelihood structure, some prior structure. And here we assume that this yields structure of x to the minus phi. Yeah? So we don't discuss in this talk finite support or compact support. We are on the, do I have it somewhere on the full Euclidean space, okay? So a typical approach, and this was already discussed in the first talk, so I can fastly go through the slide, is based on Langevin type dynamics. Here, for example, it's overdamped, and these are gradient enhanced method. So we see gradients today in this type of SDEs. And these type of SDEs usually contract, yeah, in the sense of in some TV or some Wasserstein based on some functional inequalities. As a typical, I brought here one example based on these logarithmic Soloviev inequalities that are implied by some Bakri-Emmy arguments if the potential is strong convex, right? However, which is interesting and that's quite reasonable and is connected to this generative modeling approaches, that if I take an arbitrary potential or this density and convolute it with a Gaussian, then for T large enough, also this convolution admits some functional inequalities. So given an intuition why this generative modeling might work in this mean field limit discussion. Okay, the problem is, however, that the potential usually doesn't fulfill or it doesn't yield a density that admits its functional inequalities. For example, we are not in a convex case or we fully nonlinear, think of multimodality, etc. in these resulting densities. And hence we need a more flexible approach that is not treated already by Langevin dynamics. As a comment, I want to stress out there's no free lunch. In my opinion, we will never be able to sample from an arbitrary density. We need some structures, right? And this is already the case for 1D, given by problems of localization. Or in high dimension, we have this causal dimensionality, an approximation, aspects, or also of localization. And moreover, in the Bayesian context, maybe not related to imaging, but if you have the forward model is based on some physical model, the evaluation of the potential might be super expensive, and you want to have a reduced evaluation of these guys. Okay, these are the main obstacles. So let's go to the generative modeling part. So we start with a very simple process. Many of you saw it already, the own-bit process. And this is a special type of Langevin dynamic, where the potential is quadratic. Hence, its gradient is a linear guy, yeah. And we know that what we saw by this LSE argument, that this will exponentially converge to a standard Gaussian distribution, right? And which is nice. Now we can use this only process and start in our target distribution, let's say, for this moment. Then we can start here and converge to a Gaussian. And we know many things about this process. For example, the transition density is of Gaussian type for fixed point x0, right? And this is used if you sample or make this score matching approaches or stabilized score matching approach, e.g. by Sebastian Reich and all. Okay. So now we come, I call it the heart of generative modeling. This is the reverse process of this Ornstein process due to Anderson. That is, we have this Ornstein process xt, and now the reverse process, I denote as yt, is given as follows. So we have here for a parameter lambda, still a Brownian motion, but here is a new ingredient that appears in the drift term, and this is a so-called score, right? And the score is nothing else but the gradient of the log pi, and pi xt is the density of the process x at point t, right? So if we would be able to have access to this guy, we now could start, let's say, in this xt distribution, which is close to Gauss, I'm hand-waving arguments, starting this process and end up in a yt where y at capital T now is our p star distribution. Okay, that would be ideal world. Yeah. The thing is, I have here this parameter lambda inside, and this kind of generalize this reverse STE to and links it to the ODE, right? So if I put lambda equals 1, we have no stochastic movement here, and we are just in the flow ODE case. And I brought it here because Theo is also talking in the afternoon, discussing the sampling quality between and the link between ODEs and STEs, and we see that discussion in the afternoon. Okay, so what we have now, we have this score. We are able to sample from the target density. Finish. Okay, but now we don't, of course, don't have the score. So what can we do? As I said in the beginning, if we are on this generative model setting, usually we have data. We take the data of the target, we noise it with Gaussian, and we can make some score matching type and have this strategy. However, we are not in the scenario where we have samples. So we kind of have to change with a different approach. One would be to solve associated Fokker-Planck equation, right? Which is kind of complicated in my head because you have constraints. Since you want to have a density, you want to have like energy conservation, mass conservation, etc. However, if you put like the log density, all these ingredients might be irrelevant. And in the end, we're also kind of rested in the gradient, so we don't even care about constants or normalization constants, right? And all these limits might be reduced of this guy. And this yields now this Hamilton-Jacobi-Bellman equation. So what does it mean? We take the so-called value function Vt, defined as a log of the density, or the negative log of the density. Then the associated Fokker-Planck that we saw in this Lange-Van or the Ornstein process becomes this type of equation. So we have here Laplacian. We have this weighted gradient, which is a linear operator in V. And we have a nonlinear operator of the gradient of D. Now, this is exactly Verstheim AJP equation. This is a link to optimal stochastic control, as was pointed out by Julius and Lorenz in recent work. And what's now important to note that this here, the dimension parameter is a constant. And we don't care because we're interested in gradients only. So we just skip it for the remainder of this talk. And note the right-hand side now is a AJP right-hand side. And note that we start here with a potential phi. Okay. So we are starting with phi, and we're now interested in the evaluation. One key observation is that this function Vt, as it approaches infinity, we know it converges to a standard Gaussian, right? So Vt necessarily needs to converge to x to the power of half. This is a polynomial, and this is a starting point for the next idea. So we have the score, and we want to approximate it in a suitable approximation class. This is a very open question, I would say. So usually people use network approximations to hopefully have a representation class. So we skip for another one. We need, and that is much more important, that was auch closely related to the discussion we had in your talk, can we use networks and use Riemannian-fold steps? I think with networks is very complicated. If you have some sort of tangential space, how would you add neural networks? So one closed strategy would probably extend the network, double the size. But in closed, it's a very complicated discussion maybe. So if you're able to have this right hand side and evaluate it for this function class exactly, that would be ideal situation. And we somehow need some spatial discretization classes and moreover important in the end, once we have this value function Vt, we want to have access to the gradient. And this should be ideally, this is for the stability of this sampling process, be accessible exactly. Yeah, so we don't want some trace estimators, we want an exact gradient ideally for the gradient. And this brings me now to this approximation class of functional tensor trains. Okay, one motivation maybe for the rest, so we assumed already this regularity. We may assume that we can write this potential in some sort of polynomial chaos expansion, right? Where we have descent decay coefficients. And this might be linked, if you think of some UQ setup of PDEs, to some regularity of the underlying PDEs, right? You have some smoothness, anisotropic smoothness, so you have certain decay. Or the other framework, you're in a setup where you have limited data and your Bayesian inference is not really informative, right? So you stay close to the prior. So maybe high order modes in stochastic dimension stay close to the prior, right? So we still have these in the limit Gaussian, say, near structure. Okay, so what is a tensor train or functional tensor train? So we call a function to have a functional tensor train of rank R if we may decompose a function with multivariate into a product of matrices, right? And what does it mean? So we have here a function with f1, which is basically a vector of rank 1. With this contraction of rank 1, it contracts with this component of this function, and so on and so on. Yeah. So you can think of it as a generalization of singular value decomposition in function space to the high dimensional case, right? The remark SVD does not generalize to the high dimensional case in a closed model class. Yeah. So this is a closed model class, important for the optimization. And as an example, if you have a function that is a sum of function with univariate dependence on the coordinates, then this has only a rank 2. What does it mean? I mean, if you have a density that is independent, yeah, its log is basically just a sum, guys. So exactly in this scenario, right? And this is exactly the case for the limit distribution, the Gaussian. Yeah? So what we now have is a polynomial in the limit, and we have a low rank polynomial in the limit, right? So this is a good selling point for now. Okay, so we can introduce some discretization. That is what tensor trains now do in practice. You usually don't work with a functional point of view, except for the theory. You do some discretization, and you have some algebraic tensor here. You introduce some approximation class, and you have some tensor. And now this tensor needs to be compressed, right? It's a high dimensional object. And what is naturally the case, that if we have this representation and we know the functional tensor train rank, then we actually know that we can decompose this tensor, yeah, again to a product with a rank that is bounded by the functional rank, right? So this is closely related to this functional decomposition. Okay, what does it look like in practice? So you have a tensor, you can interpret it as a graph, right? Where each of these output dimension represents one of the modes. Storage cost scales exponentially. If we are able to represent it as a tensor train, we have kind of this product structure. Here is a contraction, and each of the algebraic tensors has its own output mode. So what we can see here, we have an exponential scaling with the dimension, and here it only scales linearly once such representation is available. So what we can now discuss with this tensor train format is how does the right-hand side of our Hamilton-Jacobi-Bellman equation behaves. This is simple observation. So if our potential is decomposing as a sum, then does the right-hand side. I mean, it's clear because the Fokker-Planck equation somehow preserves this independence, right? You start independent, you stay independent until you hit the Gaussian. Okay, next observation to understand is if you take a Gaussian potential of arbitrary, covariance matrix, then you can show somehow linear growth of the ranks. So it's modularly computable for this problem class. Okay, so now let's go to the algorithm. So we have now recall this Hamilton-Jacobi-Bellman equation. So we now do some type of projection, because this operator here is a nonlinear one. If you start with polynomials, it will increase our polynomial degree. So we introduce some sort of projection to stay in our spatial discretization. And this we call the projected HB equation. And what we now can intuitively show, that now we are on the function space level, we can put it on the algebraic level, introducing these tensor train formats, right? That is, the projected HB is equivalent to a tensor valued ODE. Okay, so we level now from the function, and now we're on the coefficient level. And this is nothing else but the coefficient equation for it. And what we can show is that here, inherited by the functional representation, that this ranks, if this is a tensor train, the ranks of f of a stay under control. And now we are just up to solve this ODE. We did it by some adaptive explicit Euler method. You can think of high order methods or some dynamic lowering integrations to solve this, and where we have control over ranks, degrees, control. And this brings us to numerics. For example, we start with a Gaussian for the validation test. So we start with an arbitrary potential with a random matrix here in 10 dimensions. And what is observed is, since this is a Gaussian, we know the ranks explicitly now. So we can force maximum ranks in the approximation. We do up to truncation, we will not introduce any special discretization error, right? If you're a Gaussian Fokker-Planck, it will stay a Gaussian. So we have no discretization error in space. So we can here fully focus on the time discretization. So, and that, I mean, as we would expect in parabolic PDEs, time discretization may lead to reduced error of the potential and of the score itself. Okay. So how does it look like in the covariance ranks? So this is what we see here. Is C time. So first is the ingredient, the time of what we solve our parabolic equation. Here we see the individual rank things. What we see is in the beginning, we start with an arbitrary rank Gaussian. So we have this type of stair type linear grow of ranks that we solve with this Gaussian case. And then in the end, we know it's a standard Gaussian. So the rank must be 2, right? And this is what we behave, but we see how the ranks over time here in colored behave. They fall down to 2. And so we have control for Brownian norm towards the Gaussian distribution. So considering maybe a nonlinear problem that is out of the scope of this log concave problem, where we consider potential that is given as a sum of individual potential with own difficulties, let's say. I call this guy phi1 banana, and we will see why. I think everybody who saw some paper of Mazuk knows this distribution. We will see in a short. So it's basically take a Gaussian and you push forward it through some quadratic function transport map. We can consider multimodal, non-certainty multimodal or high order multimodal things with higher polynomial degree. And again, what we see here, color plot, we have control over covariance errors. Here's maybe a discussion. I skipped it a bit about this solving time of our parabolic equation or of the ODE. How we affect of linearized right-hand side both in the eigenvalues and how this affects the step size choice and how the step size evolve over time. And here's to note that with this on-chain processes, you usually start with a very complicated density. Then you have a very small, very stiff regime where you immediately jump to a Gaussian, and then for a long time, high metric, nothing happens anymore, right? So it's really the hardest work is to kind of make high resolution in this first stiff part, right? And this is what also interests me when you have the score matching. How do we sample from the time, what we saw in yesterday's talk? Because I mean, the first regime, this is the most important where the most errors may appear, right? Okay, so that brings me to just to this algorithm of to sample and maybe to a discussion we yesterday had also on the Blackboard. So usually people use Euler-Mariano discretization of the reverse process. Here now the score appears to reverse time. And then what's done in practice, actually, that they do some type of Langevin post-processing, right? And what means Langevin post-processing? So instead of the reverse process here, you just take this score as a potential for the Langevin, which is time dependent, and do with this fixed potential some Langevin to hopefully increase the sample. Yes, so here now the picture, this is the name of banana. And we see like if we start with the Gaussian and it travels through. And we see here, I would say still some fluctuation which might be related to discretization of the score. And this is what we should discuss in the afternoon in the talk of Theo. Okay, so what we saw today is an, I would call it efficient sampling method for moderate dimensions that is based on the notion of these diffusion models that we saw with the on-chain Unbricht processive reverse processes, where we as this score learning was now driven by some optimal control based PDE and its solution. Yeah, the so-called Hamilton-Jacobi-Bellman equation. We talked about functional tensor trains as a compression tool to sort of solve these high dimensional PDEs. This class, it enables exact evaluation of the gradients, right? We saw there's just the function basis. We can evaluate the gradients of this function base, and then it's basically just a contraction of this basis function towards the algebraic tensors again, which is very cheap in practice. We solved this ODE with an adaptive tensor specific solver. And yeah, as I mentioned in the beginning, this is a strategy we use for solving inverse problems in Bayesian context, right? As a future work, and maybe also as a remark here, is we discussed about the rank, right? So which functions actually allow for some low rank? What I can tell you, we saw the limit, it has low rank, and I can tell you for a certain class of potentials, the phi in the beginning is a low rank or has a moderate approximative rank. But what happens on the trajectory? So it's completely not clear how to analyze it for the moment. So the question, what we see in the, what I conjecture is that somehow the rank is somehow bounded at the maximum of both of the ingredients. I mean, why is the maximum intuition? You can start with a density that has, where the log potential has rank 1, right? This is not independent, but the Gaussian inner limit is rank 2. Yeah, so it must be somewhere in between. It's really open question. Moreover, we here introduce some spatial discretization on a compact domain, or you can make it a weighted domain as done in this score matching type. However, maybe we are only interested to have accuracy along passes, right? Or more, let's say, cheaper algorithm, meaning that, I mean, I have to approximate the full potential on the whole domain, but maybe it's not relevant for my later SDE, right? So it might be more specific to have it control on pass. And this is now a new project we start with Lorenz and Julius. And moreover, on this, I think, and this we saw in your talk, we are not interested at all at some points for the samples, but maybe in quantities of interest. So more, for example, if you have quantities of interest that are associated with integration, right? Then you can ask for, what can I do with these somehow samples? Can I improve the accuracy of the resulting evaluation of the integral? And this is maybe linked to importance sampling. And the thing is, if we have access to the score, or even more important, to the value function, right? I have access to the score, I have somehow a velocity field, right? So, and then I can use this velocity field. I can use the density value propagation ODE in parallel. I solve these guys in parallel. And what I now have, I have my actual process, which is actual density evaluation. And now I can do an importance sampling with the Bayesian exact density, and I have a natural reweighting, right? So given that we have some closeness of this resulting sample propagation of the AHB, we can drastically improve sampling from Bayesian inference. And that's all. Thank you for listening.